So another way in which we can start to look at extreme events and analyze them is by using a circulation-based approach. And what we do here is really define the event in terms of the circulation rather than in terms of the impacts or the meteorological phenomena that we're witnessing. So rather than saying we're looking for extreme surface temperature, we might be looking for the circulation state that caused that. We believe is sort of linked to that extreme temperature. So what we might do is take sort of well-known patterns of different kind of weather regimes. Here I've shown some examples for over the UK. These are sort of standard Met Office UK weather regime patterns that can be used. And what we do is saying, well, given that we had this particular circulation state, we know what circulation we had when the event occurred, then what is the distribution of that particular extreme variable? And this way we can start to separate the effect of the dynamics in terms of the circulation from the thermodynamics response. So here's an example of the circulation based approach using circulation analogues from a recent paper. So here you can see that this again is looking at a particular European heat wave. The extreme event is observed in a particular variable, in this case temperature, over Europe, over the sort of black box. And they've then looked to see what the corresponding circulation in terms of 500 hectopascal geopotential height is, as a sort of a trended pattern. And then they look in their analogues to see which are the best circulation analogues, which are most similar to the observed circulation. And then they subset the ensemble to see, well, you know, for those days that had circulation that was similar to the observed circulation from our model. So this is in the model simulations. You know, what was the response on the temperature in Europe in this case, to see how that is affecting what role that circulation played in the extreme event. So again, here's another example. Again, is one of these sort of groundbreaking papers by Catio et al. In 2010. And this was looking at this time a cold winter in Europe. Sorry, lots of European examples in this, I'm afraid. Again, the event's been defined in terms of the circulation state. They've classified the circulation states by using a regime classification, and then identified from the reanalysis data or model data when they have circulation that is similar to the circulation patterns that they saw in the from the regime classification by a sort of clustering analysis, and look at you know, what the difference is in the response. And here the difference between the observed response and what we would expect from the circulation analog tells us something about what the thermodynamic signal of the event was and what effect that had on the particular extreme. So it's sort of separating or partitioning the effects of the thermodynamics and the dynamics. Now, obviously, we don't have to use just a single approach when we're looking at classifying or studying extreme events. We can use, and people often do, a combination of these different approaches. And in some ways, I think I'd advocate using as many different approaches as we can, because then you get a fuller picture about what was happening with a particular extreme. So here's an example where we use both the risk-based and mechanistic approaches to studying extreme heat wave in China in 2015. And this is a paper by Nico Frechet and myself and Simon and others. And this is where we ran on large ensembles, sort of including with sort of all forcings in them. That's the actual ensembles. So they are as observed. Then maybe with the effects of only greenhouse gases. There's sort of blue ensembles on this return time plot, and the sort of green ensembles, which are where only natural forcings are included, and human-induced climate change is not included in the simulations. So you can see broadly there's a separation in difference between where we're seeing these the lines on this different return time plot. However, what we also did was separate for the particular sea surface conditions for different years. So one, we used sort of 2014 conditions, which was before the El Nino event in 2015 occurred, during the El Nino event in 2015, and after the El Nino event. And so we can see that perhaps, by not including the effect of anthropogenic aerosols, that the warming may have been even worse in the greenhouse gas only simulations, so that actually the aerosols are present and mitigating the sort of already existing effects of climate change. The presence of El Nino actually increases the likelihood decreases the likelihood of the events from occurring, and we can see that really these differences between the different sea surface temperatures that we used, the different sort of large scale circulation patterns, are actually fairly similar between the different sets of simulations that we used. Another great example, this is actually a synthetic example of illustrating things, but there are actually sort of papers that have tried to use this, and this is one by Robert Vertard et al. In 2016, and this is using a combination of both the risk-based and circulation approaches. And this is really trying to get to the nitty-gritty of disentangling the dynamic and thermodynamic components. So in this sort of illustrative figure, each of the different quadrants depicts a different flow regime. So one of those different circulation regime states. And then we can look at sort of conditional probabilities, probability distributions for each of those circulation states, and then analyze the differences between those. So we can start to sort of unpick the differences between the dynamic and thermodynamic components to the event. So you can see how actually combining these things could be a really powerful tool in order to help gain some more information.